This is the Raman spectrum of pure ethanol. You can see it looks a lot like an infrared spectrum. Our Raman shift here, we're measuring in wave numbers from 3,200 wave numbers down to about 250 wave numbers. So we're covering the same vibrational range as we do with infrared. And then our intensity, our scattering intensity is measured on the y-axis. So again, wherever you see a peak, that means there's a vibration that takes place at that frequency, at that particular wave number. And so this is the spectrum of pure ethanol. You can see the strongest band here is at about 875 nanometers. This is most likely a CH bending motion. And so, as we do with other kinds of spectroscopy, we typically will take the measurement where we get the strongest signal. So today, when you measure your standards and sample, we're going to record the intensity here at 875 nanometers, or excuse me, 875 wave numbers. Our x-axis is in wave numbers. So you can see the spectrum of ethanol is a pretty simple spectrum. And so we have a limited number of bands. The bands are quite sharp and they do not overlap very much. So that allows us to do just a simple XY regression, a simple linear regression between concentration and the intensity that we measure at 875 wave numbers. Okay? Now the other advantage of Raman spectroscopy compared to infrared when we're working with aqueous samples, as we talked about in class, this is the spectrum of water. Okay? So if we look at the spectrum of water, it's almost a flat line. So if we come over here to about 875 wave numbers, where we saw the strong signal from ethanol, there's essentially no signal at all from water. So that is an advantage of Raman over infrared when we're trying to measure organic substances like ethanol in an aqueous solution. If we were doing infrared, remember we said there's a very strong OH band out here around or above 3,000 wave numbers. So we would see a very strong band from water that would interfere with our measurement. In Raman, water is almost transparent. Hardly see the OH bands of water at all. So it is much easier now to measure the ethanol in water because at the frequency, at the wave number where ethanol responds, we have essentially no signal at all from water. And that way we don't have to subtract out or try to remove the interference from water. It's much simpler to measure the ethanol in the presence of water using Raman versus mid or near. Okay. So what you will do for your standards is, as we prepare our standards, we'll scan the standards. You will then measure the intensity of each standard at 875 wave numbers. We'll put that information into a spreadsheet, and then you can, or I will post the spreadsheet so you can use Excel then to do the linear regression, get the slope and intercept value, and then we'll also scan our two samples and put that information into the spreadsheet, so then you can take the intensity value of the samples using the slope and intercept that you calculate from the regression. You can predict then the ethanol concentration in the two samples and see how well it agrees with what the label says. Okay? Now, when you record your data, use the wave number that gives you the strongest signal. And you may see in the samples that are mixtures of ethanol and water, this band may shift by a couple of wave numbers from 875. The reason for that is we get some hydrogen bonding between ethanol and water. Here we have pure ethanol. When you dissolve ethanol in water, we get some hydrogen bonding that occurs between the ethanol molecule and the water molecule, and that hydrogen bonding may be enough to slightly shift the frequency of the vibration. So usually what we see is it may shift to slightly lower wave numbers. So your peak may shift to like 873 or 871, but use the value, record the value that has the highest response, and what we see is perhaps a shift in that band just a little bit, the shift of the peak location due to the hydrogen bonding between ethanol and water when we're working with aqueous samples. Okay, I think that makes sense. Okay, so that's what our spectra of the two pure compounds looks like. What you will do, let's go back over